We're going to be doing hypothesis testing for the rest of the semester. But in this case, we're going to be testing claims about two population proportions. Later on, we'll get into the case where we're dealing with population means. Someone makes a claim about two population proportions. Here's how the test works. We have one population here, population 1, and then we have another one over here, population 2. These have to be, disjoint populations. We don't want people from both populations to be in here. So these are kind of independent or disjoint populations generally, males and females, Christians and non-Christians, those with type O blood, those with type A blood. They're mutually exclusive groups. You don't want to have subjects in both. Then we're going to take a sample from the first group, and then a sample from the second group. So this is about proportions. So from this sample, we're going to identify, and let's just say this is type O blood, and this is type A, just to give you an example. In the coronavirus, some of the earlier studies that they've done, I think I mentioned this before, is that you're more protected from the coronavirus if you have type O blood versus type A blood. In fact, if you have type A blood, you're more likely to get in trouble with the coronavirus. It's more likely to take you down. It's more likely to kill you if you have type A blood than if you have type O blood. I don't know that they can explain that now, but that's what they're finding. All right, so we identify the number who have type A blood out of the total number in the sample. Men and women and various other things. All right, and then with these two numbers, we can calculate the sample proportion just by dividing the X value by the N value. So that's going to give us one sample proportion, the sample proportion from the first sample. Over here, we're going to do the same thing. We're going to take a random sample of the type A blood folks. And we will calculate the sample proportion over here. Now, if the sample proportion from the first population is about equal to the sample proportion of the other population, then that might give us evidence to say that, well, probably these two population proportions are the same. Remember, we're taking one sample. And we know that 95% of the time we'll get a representative sample, but there's also those 5% of the times where we get an unrepresentative sample. So we need to distinguish between the first population's summary statistics and the second. So here's where we're going to use subscripts. So x1, n1, p1 hat is equal to x1 divided by n1. And then for the second population, we're going to use the subscript 2. So x2, n2, p2 hat in this way. The population proportion up here, we will call p1. And the population proportion up here is p2. The proportion in the group of all type O folks who actually died. And over here is the proportion of type A folks that died from the coronavirus. All right, so that's the setup. So you can see we have 1, 2, 3, 4, 5, 6 variables, right? A lot more. But that kind of sets the stage. And generally, the decision we're going to make is if we find the sample proportions are close together, then probably the population proportions are close together. And we'll make our decision based on these sample statistics. All right, let's go through the 5 steps of a hypothesis test, just so you can see how they're a little bit different in this context than if we were dealing with just a claim made about a single population proportion or a single population mean. So the first step is always to write the hypotheses. And so we say H1 and H0 like this. Well, it turns out This handout here, I used to give these to you in class, and I would just give you the formulas that you're going to need for that section, so you don't have to go hunting them down in the homeworks in the textbook online, the e-text. Just gave you this formulas. So here's one for section 11.1, and down here they talk about the 3 different types of tests: two-tailed test, left-tailed test, and right-tailed test. But notice every single one of them is exactly the same for the null hypothesis. The null hypothesis is always a statement that there's no difference. In this case, we're going to assume that those dying from the coronavirus who have type O blood is going to be the same as those who die from the coronavirus with type A blood. So there's always a statement. So the nice thing about this test is that the null hypothesis is always the same. There's no difference. It's always going to be P1 equals P2. The alternative is you're going to either use the not equal to, the less than, or the greater than, and that's kind of similar. And this will depend upon the claim. Again, the claim can go in the null or the alternative. It really depends on what the claim is. And it's really important in this case that you define the variables. There's no reason for anyone to know that P1 deals with type O blood and P2 deals with type A blood. So you want to start off with the word proportion. Proportion, you know, type O blood. And then proportion of those who die from the coronavirus with type A blood. Very important to define the variables. So you're going to have a little bit more work in this step defining the variables because there's going to be 2 of them as opposed to just 1. All right, the second step is to identify the level of significance. There's no change in this step. That level of significance is typically going to be given to you in the problem, and if it's not, we're just going to establish alpha to be 0.05. 3 is the test statistic and the p-value. And again, we're going to use a calculator for function to find this. The calculator function that we're going to use, well, instead of having just a, 1 proportion, we have 2. We're comparing 2 proportions. We have 2 sets of summary statistics up here that we need to report. And it turns out that the sampling distribution is a Z distribution, and we're doing a hypothesis test. So the test statistic will be Z in here. Our author uses Z0, the calculator function just uses Z. And then the p-value. And you want to get these 2 from this test. What do you have to provide it? Well, it turns out that we don't have to say anything about the null hypothesis. Before we had to say, that the number in the null hypothesis was 0.43. Well, we don't have a number up here. In fact, the null hypothesis is always the same. So this step is just omitted. But what we do need is x1 and n1, x2 and n2. And with those 4 numbers, they can calculate p1 hat and p2 hat. Oops. Now down here, we do need the a statement about what's in H1, because we can have a 2-tailed test or a left-tailed test or a right-tailed test. So that down here is always gonna remain. So you have to select one of these. Not equal to P2 or greater than P2 or less than P2. I don't remember what order they're in. And you'll select one of those dealing with the alternative. And then when you calculate, it's going to return the test statistic and the p-value. Well, let me just write the test statistic down here. And just to show you, on your sample notes, here it is. This would be the difference. So you're really doing a test statistic. It's like a z-score. You have the sample results minus the population results. And the results we're talking about here is the difference between the two. And then down here is a standard error term that we would use in this setting if we had both P1s and P2s. I will write it in a slightly different way, but please note that we're going to rely on the calculator to calculate this test statistic. But I do want to give you the formula. All right, we're going to take P1 hat and subtract P2 hat. If there's a big difference between these two, then it's more likely that there's going to be a difference between the two population proportions. And a big difference up here would force the numerator to be big. And if the numerator is big, then it's going to make this overall fraction big. And if the overall fraction is big, like just think about a z-score of something big like 3 or 4, that means we're 3 or 4 standard deviations above the mean. And that's an unusual difference. So we're actually, the statistic that we're finding the mean or the population proportion for is the difference, or the z-score for. And then we take the difference there, and then we subtract the difference in the population proportions. So sample results minus population results over the standard error. Now the other thing that we notice is that since we are assuming that P1 and P2 are equal, if you take P1 and P2 and subtract them, this part of it is going to equal 0 because of our assumption. You subtract two things that are equal, the difference will be 0. So normally this doesn't even appear. All right, and the standard error term is, you know how we had PQ divided by N? Same thing here, but it's P1 Q1 divided by N1. And then they're just additive. Turns out that this works out, N2. And we add those two under a square root. This is all we had right here in the single proportion case. In the double proportion case, we just take this and then add the other one. The other thing I should mention is that in order to have a z distribution, we need NPQ to be larger than 10. That tells us we have a big enough sample size. Well, what we're going to use here are the sample proportions. So N1, P1 hat, Q1 hat, that has to be larger than 10. That ensures we have a large enough sample that we've selected from the first population, but we also need that N2, P2 hat, Q2 hat is also larger than 10. If both of those criteria work, then we have a large enough sample size and we can assume that the sampling distribution is normal. So we could use the z distribution. Most of your problems would just normally be like this, but you might be asked to check a couple of problems that these conditions hold. All right, if we assume that P1 and P2 are the same, then you can see that these two fractions here are exactly the same. So another version of it that you might see is top P1 hat minus P2 hat, and then divided by, well, I'll just leave it that way. You can look in the notes and you can see that this version here, if P1 and P2 are equal to one another, simplifies to this. This is P hat, Q hat. Maybe I'll just use Q hat here. And then 1 over N1 plus 1 over N2. All right. We won't use either one of these, but algebraically, if P1 and P2 are equal, this is equal to this. And the P hat we're talking about there is the pooled proportion. So you add the frequencies of X1 and X2 and divide by the sum of the sample sizes. This is kind of an overall, if you kind of, instead of treating these two as two individual samples, just treat them all as one sample, combine the results, and this is what we call the pooled proportion. So if you see this in the output of this here, it's kind of a pooled proportion. It's going to be somewhere between P1 hat and P2 hat. Okay, step 4, decision, no change. And 5 is the conclusion, and there's no change here. So the way that we make the decision is P is less than alpha, implies that we're going to reject the null hypothesis. That doesn't change. In the conclusion, the way that we interpret it, the decision is going to be very similar to what we've done in the past. There's evidence for, there's not enough evidence to say that those with type A blood die at a higher rate from coronavirus than those with type O blood. Abstain from alcohol. In October 1947, so way back when, this World War II ended in I think 45, and then a couple days after that, the Gallup's organization was around back then, and they surveyed, all right, so 1947. Back in 1947, they surveyed 1,100 individuals, adult Americans, and asked, are you a total abstainer? Or do you on occasion consume alcoholic beverages? So do you consume alcoholic beverages or not? And they didn't go into the frequency of consuming alcoholic beverages. Of those 1,100 adults surveyed back then, 407 indicated that they were total abstainers, did not drink. So if we actually calculate that proportion, that would be P1 hat, and divide those two numbers, we get 0.37. So 37% back in 1941 said, nope, no alcohol for me. All right, then we have in a recent survey, so let's just say that this is 2019. 2019, they took another random sample last year, and they asked the same question. They also asked 1,100 individuals, Americans, and they found that 333 said, nope, never drink alcohol. So in the more recent study, the sample proportion would be the 333 over 1,100. And this works out to be 0.303. So 30% compared to 37%. That seems to be a big drop in those that don't consume alcohol. Said another way, seems to be a big increase in those that do drink alcohol, moderately or excessively, it doesn't say. Has the proportion of adult Americans who totally abstain changed? So they're not saying that it changed so that there are more non-drinkers these days than back then. They didn't state the claim in terms of that there were fewer non-drinkers back then than today. They just indicate, has it changed? So we're going to turn that around and say, our research hypothesis, our alternative hypothesis, is that in fact it has changed. And so we're going to say that the proportion back in 1947 is not the same. If it's changed, then it's not the same. And the way we write that mathematically is with the not equal to sign. So the proportion that never drank in 1947 is the same, is not the same. That means it's changed. The proportion in 2019. All right, so I think we're ready. We've got the level of significance here. This is step 2. No change there. But now let's write the hypotheses. Now, as I mentioned earlier, that the null hypothesis is always the same. So every problem that you do from this section, the null hypothesis is going to be P1 equals P2. And here is our claim. So this is the alternative hypothesis, P1 not equal to P2. Has changed. Might be greater, might be less, we don't know. All right, here's where we need to define the two variables. So P1 is the proportion of Americans that did not drink alcohol in 1947. And then P2, proportion, ... in 2019. So something to distinguish, write out the definition 1, and then you can maybe abbreviate it this way, the proportion, same thing, but in 2019. That's your step 1, writing the hypotheses. Step 2, write the level of significance. Most times it's given in the problem. And then step 3, we're going to identify the test statistic and the p-value. We're going to use 2 prop z test. No null hypothesis is needed here to specify that. So we're going to go right to x1, n1, x2, n2. And then for the alternative hypothesis, we're going to write not equal to P2. And then we'll calculate. All right, here are summary statistics. Just make sure you put them in the right spot. For example, we're going to write the x value first, 407, and then the n value for the first population. Just so happens that the second population has the same sample size. So again, use the x first and then the n, and then calculate. So for this here, they will first report, well, I think the first thing they do is they write the alternative hypothesis, just to make sure that you have the right one. And after that, it's going to give you the z test statistic and then the p-value. So let's see how that works out. Stat, tests. All right, so 2 prop z test. It's right under the 1 prop z test. So number 6. So 407 and 1100, 303 and 1100, and not equal to. 2 prop z test. Be careful because there's another test function that looks a lot like this one. I'll give you something completely different. All right, when we calculate, oh wow, big. Okay. X2 is 333. And let me try that again. So, thank you, Dylan. All right, let's try again. 6. I have to change this one to 333. Okay. That look better? All right, before we leave this screen, I do want to point out one thing. The p-value is the probability of getting our test statistic or something more extreme. And since it's a p-value, it's a probability value. Probability values are always a number between 0 and 1. We had a unit in this course where you may have heard me say probabilities will never be larger than 1. So you never want to read the probability value from left to right. Because if you start writing 8.4, 8.4 is a number much larger than 1. And we know a probability value cannot be that. So read from right to left so you can see this piece right here. This is in scientific notation. This tells you that you have to move the decimal place 4 places to the left. So it's a tiny, tiny, tiny p-value, which would correspond to a z-statistic that's more than 3 standard deviations away from the mean. Here is, oh, that's probably where I got the 303 right there. This is P1 hat. It calculated it from taking 407 and dividing by 1100. And this was the P2 value, which it got from taking 333 divided by 1100. Now this number here that I told you about, this was the pooled population proportion. Let's see if I can find that number. You may recall me writing this, the pooled proportion. And I did mention back then that this number will be somewhere between P1 and P2. So if you look at P1 and P2, if you combined all the data together, this number is going to be somewhere between these two. And you can see that it is. This also says that there's more information down under, just to go see what that is. The only other thing it reports are the sample sizes. Okay, so the test statistic is 3.339, and the p-value, I'm going to write it out. (8.4011813) (e-4). Okay, so that number equals 0.1238. That's what it really equals. So be careful how you read that. You may have even encountered this in some of your problems in 10.3 and 10.2. All right, step 4, p is equal to 0.00084, alpha is equal to 0.05, and certainly this number, our p-value is less than our alpha value. P is less than alpha, so we reject the null hypothesis. And so finally, step 5, there is evidence to support the claim that we can use percentage here. The percentage of Americans that do not drink alcohol has changed. So that hypothesis means that the two proportions have changed, the one back in 1947 compared to the one today.